We'll now talk about models for population. And we'll do this using two different models, the exponential model and the logistic model. So let's start with the idea of the exponential. The basics of the exponential model is that the derivative of the population, how quickly it's changing, is equal to the birth rate minus the death rate. The basic form for any population model is going to be that the population's changing at a rate that's equal to the birth rate minus the death rate. We're going to assume that our birth rate is proportional to the population present. So how many new births are being added to this population depends on how many people we have. We'll call this K1 times P. So K1 will be our birth rate. For the exponential model, we also assume that our death rate is proportional to the population, which we'll say K2 of P. So K2 is our death rate. So this essentially assumes that the only reason you're dying is from old age. So this is modeled by dP over dt is equal to K1P minus K2 of P, which is the same as Kp, where K is K1 minus K2. Using the fact that this differential equation is separable, we can solve and get that P of t, our population, is equal to P0 times e to the kt, where P0 is our initial population that we start with, and K is once again that birth rate minus the death rate. In 1790, the population of the United States was 3.93 million. And then in 1890, the population of the US was 62.98 million. I want to estimate the population as a function of time using this exponential model. If I let 1790 be time 0, then I know this is going to be of the form P of t is equal to 3.93 times e to the kt, where P is my population in millions. K comes from the birth rate minus the death rate, which I don't necessarily know here, but I can use this other point to figure it out. Since 1890 is 100 years later, I can stick in 100 for t, and I should get 62.98 back out. And if I were to solve that for K, I would get 0.027742. Sticking that back into my model gives me P of t is equal to 3.93 times e to the 0.027742t. This does give us a model to estimate the population, and we can stick in numbers for t and look at our census data to see how well this actually works. And this is a great model up until about 1900. After 1900, we predict a population that's much, much larger than the actual population of the United States. So this isn't the best model. So now we'll look at the logistic model. The main issue with the exponential model is all of our deaths have to be from natural causes. But in reality, we have a lot more different kinds of deaths than that. So these are going to factor into our population as well. So one thing we might assume is that the death rate can also be proportional to the number of two-party interactions. In a population of size p, there are p times p minus 1 over 2 different possible two-party interactions. So this shows me how many different ways I could find a person and then another person, and how many different possible pairings I have. Since I'm now assuming that my death rate is proportional to the number of two-party interactions, I have that dp dt is equal to K1 of P, my birth rate, minus K3 times P minus 1 over 2. So the proportion times the actual number of two-party interactions. Another way to write this would be dB dt is equal to negative AP times P minus P1, where A is K3 over 2, and P1 is 2K1 over K3 plus 1. This is a separable differential equation, so I'm going to divide by P times P minus P1 and multiply it by dt. And then we can integrate both sides. The integral on the left is a different integral to do, but we can use integral tables and look it up, and we get 1 over P1 times ln of the absolute value of P minus P1 over P. On the right-hand side, we get negative AT plus C. Actually, solving for P of t gives us that this is equal to P0, P1 over P0 plus P1 plus P0 times e to the negative AP1t. This time I have that in 1790, the population of the US was 3.93 million. In 1840, it was 17.07 million. And in 1890, it was 62.98 million. So this time I want to use the logistic model to estimate the population. Using my logistic model and the fact that P0 is 3.93, I have this, which has three variables in it, P1, A, and T. T is okay, it is the actual variable of the equation, but I need to find both P1 and A. Sticking in 50 for T and then 17.07 for P, and then once again 100 for T and 62.98 for P, I then have two equations with two variables. Using software to help us solve this system, I get P1 is approximately 251.7812 and A is approximately 0.0001210. Sticking these values in, I get this population model. And once again, we can stick in various values of T and compare it to the actual United States population, and we can see that this is going to actually be a much better approximation for our population.